Hello everyone. So I would like to thank organizer to give me the opportunity to talk about my research. So just a sec. So today I will talk about the constraints on periodically driven quantum system. So the question is how to test that your quantum information processor is working fine or not. Now how to test the quality of a specific circuit. So in quantum computer there are mainly two types of error, one is coherent and another is incoherent. So what is coherent error? So coherent error actually you prepare some target, you prepare some unitary that is not exactly equal to your target unitary. So what do you mean by that? Let's say you want to rotate a qubit by an angle theta, instead of rotating by an angle theta, you rotate it by an angle theta prime. So this kind of error is called coherent error. And what is incoherent error? Incoherent error occurs when your system is coupled to the external environment. So it is important to know the difference between this coherent and incoherent error. So because the source of coherent error and the incoherent error is completely different. So if you have coherent error, that means you have some miscalibrations in your quantum circuit. So you need to do proper calibrations to make it good quantum computer. And what is incoherent error? Incoherent error, you have some extra coupling. So that means you need good isolations to make it ideal. So the motivation was to find the scalable protocol to understand the noise mechanism. So what is the rule of this game? So rule of this game, the circuit may be given, but in general the circuits are quite complicated to simulate and to know what is the output. So in principle you don't know the output. Although our original goal was to formulate the general inequalities that are customized to the periodic unitary driving, however, we found some scaling for the noise. So actually this is our protocol. What we have? We have an initial state rho 0 and we have a unitary, and we are doing measurement after this unitary. So basically we are measuring this survival probability. What is this? Let's say you start with the initial state that is in ground state, and after applying this u, you are actually checking what is the count for your ground state. So that's what it means by this R1. So R2 is the same kind of that you again measure the survival probability, but you have two u, one u and one u. So this is the R2. And similarly you measure R3 after 3 unitary and so on, you measure Rn. So this is our first finding. What we have Sn has this form, this omega k and Rk is this quantity, this Rs has to greater than equal to 0. And omega k is kind of weighted average, and it has this constant. If you take the sum of these, it has this positive and negative sign, so it leads to 0, and if you take mod of these, it will be the 1. And one can show that it has this also this monotonicity property, that it decreases like this, Sn has to greater than equal to Sn plus 1. So are there any questions before I move on? Is this fine? Okay, good. So as I mentioned that our original goal was to find this kind of generalized inequalities, but we have also found that if we take the large n for the slow changing Rn, we find this kind of exponential scaling. So these alpha actually depend on the parameter of your circuit, this depends on the u, and C0 depends on the initial conditions. So please remember this thing, these two results, because I will mostly talk about these results in my current presentation. So to start with, our assumption is this: we have a periodic unitary protocol, few examples. So few examples of this kind of inequality is this. This is S2, S3, S4. However, in practice, in the experiment, this is not the case. So it can be this or it can be this. So in the both case, one can see that your Sn is violated. So let's say you have here you have unitary, but in the middle you have some u prime. So it can also violate this, and what we have, it is kind of k means that your system is connected to the external environment. So in the both case, you can find the violations. But in the control electronics, we have a good way actually, we have a good control over the electronics. So, this case is less likely to occur. So, we disregard this case. So, if I find the violations, is because of this. So, this is one of the demonstrations of the bound that I already discussed, the SN. So, in real device, we did this experiment in IBM. So, IBM device is also not perfect. So, we wanted to prove that it is violating these bounds. This SN is getting negative. So, this is the circuit we used, and you see after some evolutions it is getting negative. So, this confirms this, you have some error in your IBM quantum computer. And this is another test that I already mentioned you, that your this one, the curve should decrease monotonically, but it doesn't. So, although in this case you see that it doesn't get negative, but it violates this one. So, this is the experiment from the IBM ROM. So, this is another demonstration that your this IBM device is not perfect. This is a noisy device. So, now I want to mention something important. Let us say in all possible cases, it is not possible to find the violations. Even if you have noise present in the system, you cannot get the negative value. So, we need something more sophisticated to analyze this kind of situation. So, for this, our second finding is this, this is more sophisticated. We have this exponential scaling. If you take ln of this, it looks like this, it's a straight line. So, this is our experimental demonstration. So, you see this is the same circuit what we used here, and this green one you see, this is actually the simulated one. If this circuit is perfect, if you do not have any noise, that is how it should behave like this. But in the ROM you see it is also straight line, but it is violating from the original scaling. So, that means it has different slopes. As I mentioned you that this alpha is dependent on u, so that means it has some coherent error. But in the Melbourne, in the orange you see is deviating from the scaling. That means you have major incoherent error in this device. In the later I will actually explain how to quantify this error. So, this is here I am just explaining, this is deviating from the scaling. This has some noise, but I will show that how to quantify the amount of the noise that you have. So, this is the result from our collaborator from University of Maryland. So, in the first experiment what they did, they took this circuit, this is the U, and they repeated our periodicity protocol. So, this is the U they took. So, the black one you see, this is actually the simulation one, and this one is actually what they got from the experiment. So, now we wanted to understand how this one is actually close to the exponential scaling. So, what we did, we do a fit with the exponential with the experimental data. What we find that this is almost 0. So, it is almost having this scaling, and this is the difference between the theoretical one, this black one and this blue one. So, actually the difference between these two plot is because of this coherent error, because you have this exponential scaling, but with different slope. In the second experiment, what they did, they have actually way to put incoherent noise. Like they have this optical pumping, they can put this noise in a controllable way. So, this one that you see, this is the difference between your fitted one and the experimental one. You see, this is the pink dotted line is actually the when they didn't add any kind of noise, okay. And this scale you see in the y-axis, it's every value is divided by 1000, okay. So, what they did, they intentionally changed the calibrations, they miscalibrated their device. So, that's what you see by the triangular, this one. So, you see it is almost lying in the top of this. So, as I mentioned, the coherent error does not change the scaling. So, this confirms this from the experiment. And this large lifetime means you have a large amount of the error, amplitude damping error. So, you see this is for some value is deviating from the scaling. So, the plot you see in the right is actually this is the zoom out version of this. So, in this plot it is not possible to see. So, you see this 5 millisecond lifetime, it is such large incoherent error, it is deviating a lot from the scaling. So, this experiment actually confirm our theoretical predictions that what we mentioned, that if you have incoherent noise, you will deviate from the scaling. So, now let us understand why we have the exponential scaling. we can actually see like this. So, to understand this exponential scaling, we need to know about little bit of the Liouville space. So, I will give a brief introduction of the Liouville space. So, you have a density matrix, n by n density matrix. You vectorize it, you just stretch it and make it a vector, and the expectation value look like this. It's like inner product between A and rho. So, this is the equations of Liouville equations of motions, and it takes this form in the Liouville space, and H is the Hermitian. And if you have periodic driving and with the same unitary, then after the kth evolutions, one can write this u will k to the power a rho 0. And this is the RK, this is the inner product between the rho k and rho 0, and this is the RK. One can show this U dagger as related to the actually inverse protocol. So, you see that one can see that RK is equal to the minus RK. This is very important. Please remember this thing. I will use this thing in the next slide to prove the SN. Okay. So, the main idea is to construct a positive operator in the Liouville space. So, this is one of the way. This UL is the evolution operator in the Liouville space. And if this is a positive operator, it's trivial to see this has to greater than equal to 0. Moreover, one can actually verify this eigenvalue of the G is actually bounded between the 0 and 1. So, this is actually confirmed by the factor 2. So, if okay, this is not that interesting. If you take nth part of this, so if you take the any positive power of any positive operator, it will be also a positive function. So, it is also positive, and if you put the value G and you expand it and you use this one that I already showed you, this RK and R minus K is equal, then you get this the conditions on SN, it has to positive that I showed you. Now, let's prove this exponential one. So, if my operator G is a positive operator, then actually G has to be written like this, and if you take nth part of this, it has this form. You see this lambda is less than 1, so it has this all decaying modes. So, in the large time limit, if you take n is very large, then this is the only term it will contribute to the sum, other term will just vanish. So, the slow decaying mode will prevail. Okay. So, this is the reason why we had this exponential scaling. And using the same methodology, one can prove this monotonicity property that Sn has to greater than equal to 0, and this convexity property of the Sn. So, now let us talk about something about this Markovian noise. When you have Markovian noise, this is our just unitary part, this is in general, this is Hermitian, and this is not Hermitian. If you take X of this form, and if you have periodic quantum Markovian evolutions, then one can show that H2 has this form, H3 has this form. Okay, so in general, however, one can prove that Sn has this kind of a scaling. So, this is, you see, this is a factor, this is not exponential, this is on our end when you have periodic Markovian evolutions. And this is the quantity that is related to the purity I will talk about in the next slide. This is just a constant. Just a second. Sorry. Okay, so actually our method can be extended when, let's say, you have some accessible system, but you don't have access of the whole system. In that case, you can show that it also follow the exponential scaling when you don't have any noise. Let's say this is the scenario. Okay, this is your accessible system, and this is the state which are in the completely mixed. And in this case, you have this is accessible and this is accessible. These are not accessible, and you measure they are there. Okay, and if you plot this SN, you will find this exponential scaling. But if you have a noise in this inaccessible region, then it doesn't follow the exponential. It follows this 1 over n. What I showed you, that if you have Markovian noise, it will follow this scaling. So, this is our actually the simulation result. We took this circuit, this interactions between the two qubits is sigma x and sigma x, and we have a sigma x, and this is the state we put it in the ground state, and this is the completely mixed state where we put noise. If you see in the first plot, when you don't have any noise, then actually you have this scaling, and if you take the discrete derivative of this plot, because this is a straight line, it has to be also a constant. So, you see this is getting the constant value. And in this case, what we did, we put some small amount of Markovian noise, and you see from the discrete derivative of this plot that it's actually growing. So, it doesn't follow the scaling because you have Markovian noise. So, this is one of the confirmation from our simulations. Okay, so they did this experiment in the iron trap. This is the circuit, and they use these two circuit, and they take the average of these two circuit, and they showed that exactly they don't have any noise here. So it follows this exponential scaling what we found out theoretically. So now I will tell you the story how to extend our formalism for arbitrary circuit. What I showed, this is true only when you have the slow varying Rn, but how to generalize this formalism. Okay, this is instead of, so look at this unit cell, what we have U and U inverse. And it's connected to the environment. So what is U inverse? U inverse is the pulse inverse of the U. So this makes your the unit shell. So as a whole, this is kind of a small action. But what do you want to know? We want to know something about this U. Okay. So for the pulse inverse to know about it, so see Ramstock, he will explain in more detail. So in this case, the Sn has this form. So what we had earlier, we have 1. So this 2 factor actually expresses the fact you have U and U inverse. In fact, one can show that this, if you take this quantity with the 2, then it's actually the period loss in this cycle, in this U. Actually, we want to understand about this U. Okay, this is the way how one can understand that how much you are losing the purity. So this is we have a way to quantify what is the amount of error present in your system. So the conclusions, I think I am able to motivate you that we have a formalism that is actually, we found a signature of a unitary system and a way to quantify noise. The exponential and 1 by n signature is actually resilient to the spam errors. This thing I actually haven't discussed, but it can be shown actually. Okay, so we already extended this formalism, these transition probabilities. In this talk, I only talk about the survival probability, but one can extend this formalism to the transition probabilities. So next, we want to do actually, we want to use this pulse immersion technique to observe the utility of our method in multi-qubit systems. Okay, so that's all.